Emphasizing the reflexive ideal and how we have to there might be more emphasis on recognizing that there is no that it's empathy also different ground. I do feel that I've had a lot of practice in this and there are a bit in both Orderlies and Zen as well. And my experience is that they lead to a similar outcome, but the path is really different. So like,
I was sitting here actually, looking for another seat. Okay, let me go there.
If you're doing like a self-inquiry advice with them where you're sinking deeper into bliss and presence, it unfolds differently. I think the outcome is the same, but all shows different sense of something very from the relative mind. A little bit of both. I would say the advice is around this stuff. It was mostly reading, for example, Sri Sagadata and Ramana, and the teacher was making both these are the teaching now is making or like Atmananda's his teacher was
That's where I would have been.
And so as part of that whole software, when you change the way that they apply for some years, and that was many years. I have practiced sort of like pleasurable certain places where you do certain things could be like somehow integrated into daily life in a way that you couldn't possibly do with the
This is really interesting because these are all the things I love about my teacher and his practice. I'm always trying to figure out what exactly he's doing. Just like where one of my questions he's trained in but yeah, in a way, like with stuff like one of the things that I've seen is that, just the level of integration is practically more I do go deeper in practice, it's like regardless of the way that each of us are his teacher was a guy called that's another so he did that for ages, and then with other you're now to ricochet, come over here and teach you about shit. And then they can have a show of sort of, this is really, I can do his culture up. Let's translate this into an idiom of that culture. Let's bring in very similar to what's
Okay, we should make a start. Drift into lunch if we don't. All right, next up we have Paul Redding, University of Sydney. Hello. Paul Redding speaking on Hegel on Nothing in Particular, Infinitesimals.
Thank you, Dean, and thank you for the invitation and organising this conference. I mean, it's been fantastic experience. And I was just mentioning to Daniel, I mean, I feel sort of embarrassingly sort of short on ways to sort of reflect on the experience of these things. I mean, in relation to all the speakers so far. Maybe if I start thinking about these sorts of experiences, I tend to go to aesthetic experience, and I tend to think of that in, I guess, rather Hegelian ways. To give, an example, this is sort of commonplace, I suppose. Goethe talks about it, but I remember one very strong experience that I had in this regard in the Art Gallery of New South Wales, and I just can't remember whose pictures I was looking at, but there was an exhibition of these sort of exquisite sort of still lives in a room, and I was sort of walking around from one to the other and sort of getting absorbed in them. And then I walked what I thought was the next picture, and I was actually looking out the window at Woolloomooloo, which I've sort of seen, for my entire life. I used to live in the area and so on, and of course you have that experience of never having seen this before, right? It's sort of astonishing revelation of this is a landscape and seeing it for the first time. And so they're the sorts of things that I think of, and I think of them in terms of the sort of Hegelian categories, I guess, of the notion of singularity as something that's incredibly unique, and as opposed to particularity of one of a kind, right? So my normal experiences of Woolloomooloo had been, there's that building estate, there's those things that were built in the 60s, and sort of descriptions, and, but suddenly getting beyond those descriptions. Anyway, so that's the limits of sort of my way of talking about this, and I'll touch upon the experiential bit a little bit in talking about Hegel, but not much. Let me start off just with because of the sort of brief of this conference, I thought, how am I going to get going? So I started reading around. I came across this interesting article from a couple of years ago by Sudha Bhattacharya, who turns out, I think, to be an astrophysicist, which is interesting. And it's on, well, you can see the title, and it's on a lot of things. I mean, he's talking about Indian culture, the invention of zero in Indian culture, and the fact that the Greeks didn't have a zero in their mathematics. And the argument, well, one of the arguments was that modern European culture is rooted in Greek sort of nullophobic attitudes. I don't think he used that word, I made it up. Typified by Parmenides and Aristotle. But commitments to the concept of nothingness is implicit, he said, in the use of zero in European mathematics. That's essential for the intelligibility of modern science. Zero hadn't been a number for the Greeks. It was introduced into early modern Europe via the Arabs from Indian origins. And his sort of conclusion was that modern European culture faces a type of contradiction between its nullophobic philosophical stance and its commitment to a scientific worldview. And so that got me thinking about Hegel, who's a real Hellenophile, right? Who's got attitudes which sort of can easily look racist when he talks about Indian culture, Indian mathematics even, or he recognises the greatness of Indian mathematics. He's sort of very negative towards the sort of way that plays a role in the Indian worldview. And wondering how Hegel might respond to this sort of thing. this person will come up in two contexts in the talk. I mean, he was the person that introduced zero into European culture mathematics in the 13th century. Supposedly took a couple of centuries to catch on. Maybe that does testify to this type of nullophobic background of European thinking. He's also the person associated with the Fibonacci series of numbers, which you may or may not have come across, but which will come into the talk too. They're sort of unrelated in a way, but maybe they are related. Okay, Hegel on nothing. Well, he has something to say on nothing very early on in the science of logic, which gets going with a type of triad of concepts. The first, he's supposed to be building up a body of concepts from the most obvious, right, the most immediate, and surely the most immediate, the assumption is being, because that can be said of everything, right? That's nothing without it. So surely every other concept we apply to the world presupposes the concept being. And he says it's being, pure being, without further determination. In its indeterminate immediacy, it's equal only to itself, and also not unequal with respect to another. Because it's everything, right? There aren't any others, supposedly. In its pure indeterminateness and emptiness, being, the indeterminate immediate, is in fact nothing, and neither more nor less than nothing. So that's the first sort of result of thinking about being. So he's not going to be a Parmenidean, I suppose. So then we go straight into nothing. Nothing, and what he says about nothing is exactly what he said about being, right, effectively. Nothing, pure nothingness. It's simple equality with itself, complete emptiness, complete absence of determination and content, lack of all distinction within. Nothing is therefore the same determination, or rather absence of determination, and thus altogether the same as what pure being is. Well, that seemingly is an intolerable situation, right? I mean, being and nothing can't be the same, surely. This is what we're led to think, and that's sort of, in a sense, right. I mean, we're supposed to find this an intolerable assertion. So he moves on to becoming, which is supposed to articulate these two notions. You know, what is sort of comes into being from nothing, and what is can go out of being to nothing. Right? So becoming, pure being and pure nothing are therefore the same. The truth is neither being nor nothing, but rather that being has passed over into nothing and nothing into being. But the truth is just as much that they are not without distinction. It's rather that they are not the same. That sort of intuition has to still find a role. That they are absolutely distinct, yet equally unseparated and inseparable, and that each immediately vanishes into its opposite. Their truth is therefore this movement of the immediate vanishing of the one into the other. Now that sort of starts off this progression through triads of concepts, and using one of his formulations of the sort of more general structure, it instantiates what he sometimes calls the identity of identity and non-identity. Right? I mean, being and nothing are identical, but they're non-identical, and somehow becoming is supposed to articulate this combination of the two. Okay, just to sort of give you a sense of the triadic structure of the science of logic, just goes through the whole business, right? So the book is divided, or the text is divided into 3 books, each of which are divided into 3 major parts. And when you look at each of the major parts, they're divided into 3 sort of sections. And when you look at the sections, they're divided into 3 bits, right? And as you can see, there's the being, nothing, becoming bit that starts the whole thing off. And so you've got this type of generation of triads within triads. In relation to that, there's this interesting diagram that had come up in his papers after that were sort of sorted out by Karl Rosenkranz, who was his biographer, after his death. It was thought to have been drawn at around 1800, when he was intensely interested in geometry. He was reading Euclid at the time. And apparently, according to Rosenkranz, it was meant to be a type of visual representation of Plato's world soul in the Timaeus. So at that time, Hegel was working still with Schelling, who was Hegel and Schelling and Hölderlin were famously together at the Tübingen Seminary, and this is 7 years or so after they'd left, but he was then going on to work with Schelling at Jena. So he's still in association with Schelling. And interestingly, it turns out that this is not an insignificant mathematical object, right? There was a mathematician in the early 20th century, a Polish mathematician named Sierpinski, who was interested in this, so it's called the Sierpinski triangle. And the reason why I was interested in it is that, of course, you can just iterate each division into each of these divisions, right? And you can potentially just keep on going forever. So when in the 80s talk about fractals, Mandelbrot sort of made popular the idea of fractals, those sort of patterns, I'm sure you know them from, YouTube and things like that, that just sort of infinitely reproduce. You sort of delve into these patterns that just keep on going infinitely. The Sierpinski triangle was mentioned as the sort of an early version of such a fractal. And in fact, they seem to have been used in the Middle Ages in Christian tiling patterns in cathedrals and so forth, and it's pretty obviously used as meditative type of designs, because they do give you this sense of being drawn into a sort of infinite space. Okay, we'll come back to that, right? Because it will sort of be important for what Hegel says about this problem. The problem, he addresses this in Science of Logic. And Hegel is it's sort of often not really realised the degree to which Hegel was interested in both mathematics and mechanics. And his interest in mathematics was especially about ancient mathematics. He would seem to be, for a philosopher, pretty well informed about ancient mathematics. And he was also interested in contemporary mathematics and mechanics, so the application of mathematics and mechanics. We know it from his library, for example, which we've got a list of all the books in it. And he devotes quite a bit of the first book of the Science of Logic to the problems of Newtonian mechanics and the use of calculus in Newtonian mechanics. The conventional story is that the time that Hegel was writing, so the first decades of the 19th century, calculus had been enormously successful in its practical application to physics, but it faced sort of philosophical problems stemming from the use of what were referred to as infinitesimals. And that these problems weren't really solved. And some people think they weren't solved then, till about 50 years after Hegel's death. Now, I mean, I get the sense that mechanics in those centuries, like in the 18th century, was in something of the situation that, say, quantum mechanics is in, when the Dean was talking about now. I mean, in some sense, everyone liked it because it worked, gave you the right predictions and things like that. But if you delved very deeply into it, it seemed to rely on presuppositions which seemed very odd indeed. Right? And infinitesimal magnitudes, the idea of magnitudes that were smaller than any other magnitude, but they weren't zero, was the sort of stumbling block. So how did these fit in? Well, Descartes had introduced, of course, the discipline of analytic geometry, where you get, the x and y coordinates, we still call sort of Cartesian coordinates, and had reduced things like points on lines to a combination of numbers, right? Because the x and y axes sort of represent numbers. And Descartes had the idea of real numbers. There was a sort of a number for every point of these things, although the idea of real numbers wasn't really sort of substantiated till a lot later. But there were problems with curves. And so, okay, if you, well, I should go back a bit. For a straight line, if you're measuring velocity with this type of geometry, it doesn't seem to be a problem. Velocity is just distance over time. You take a sort of slab of time, you find you look at the distance travelled, right? You know, it's simple. But once you get into talk of acceleration, which was of course what was going on, you're into curves, because acceleration is the change of velocity with time, right? So time gets squared. It's sort of, you know, distance over time, or distance over time squared. And the geometry of curves is much different to sort of Euclidean geometry. And calculus was part of the sort of solution for these sorts of problems. But the sort of solutions were all sort of odd, right? I mean, you meant to talk about velocity at a point in time on this thing. Well, what is it to talk about velocity? You know, what don't we mean the velocity is over time, right? That sort of thing. What does it mean to talk about velocity at a point of time? Intuitively, you would think that the velocity was the slope of a tangent that touches to that point. But, you know, again, what do you mean by velocity at a point? And how do you get the relationship between the curve and the tangent? Well, I mean, typical books on calculus that you have always got, usually have these sort of diagrams on top, which gives you the clue of how it's done. Sort of you break up a curve into sort of small rectilinear parts that you can measure by Euclidean sort of principles, and then you sort of do something like make all the bits get closer and closer together and think that where they end up is what you're after. Right? So Newton's got its diagram something like this. If you sort of apportion the curve into these points, well, you can get a velocity, you can get a slope of a line between that point and that point, right? There's no problem. You're in the domain of, as I said, sort of linear functions, that sort of thing. They're no problem. And then you're supposed to shrink these, they get closer and closer together. The ratios get more and more accurate as they get closer and closer together, but it leads to this problem of they shrink to zero, and when they shrink to zero, there isn't a ratio because there isn't, you know, that bit and that bit. So what is it to have a value at that point? The whole approach wasn't totally unique. I mean, it went back to the Greeks. The idea of doing things like finding problematic relations of curves, here for Archimedes, the ratio of the circumference of a curve to its diameter was solved by doing something similar. For Archimedes, you'd draw polygons within the curve, within the circle, and then outside the circle, and then you'd increase the number of the sides of the polygons, and you sort of start to get figures close to what we think of as a pi, right? But Archimedes didn't have this idea of smaller and smaller ones zeroing in on a point, which is the modern contribution by Leibniz and Newton. There are lots of philosophical problems raised with this approach during the 18th century. And the famous one, the one that sort of, you know, has survived, was by Bishop Berkeley, who was attempting to sort of turn the tables on sciences or scientific critiques of religion by saying, you know, look, there's these sort of crude accounts of science which say, I only believe in the sort of things I can touch and whatever, right? And Berkeley was saying, well, look at things, you know, have a look at your own, get your own house in order, right? The most contemporary scientific theories are committed to these things called infinitesimals, and what are they? In his wonderful phrase, the ghosts of departed magnitudes. If you sort of believe in those, you'll believe in anything, right? So, that sort of summed up the problem, and those problems, as I said, still hadn't been solved by the time we get to Hegel. So I'm interested in Hegel's take on these things. What does he say about them? Well, here are a couple of things that he says, in which he states the problem pretty clearly, I think. It may be objected that vanishing magnitudes do not have a final ratio, because any ratio before the magnitudes vanish cannot be the last, and once vanished, there is no ratio anymore. But by the ratio of vanishing magnitudes is to be understood not their ratio before or after they vanish, but the ratio with which they vanish. That seems to be a quote actually from Newton, because he sort of quotes the Latin. And he's interested in this idea of the ratio with which they vanish and making sense of that idea, and making sense of it in a type of Greek rather than a modern way. He's just as, not for the same reasons as Berkeley, but I think he's just as critical of the whole analytic approach to these things, the reduction of geometric figures to numbers and so on. He also says, because of the law of continuity, the vanishing magnitudes still retain the ratio from which they derived before they disappear. Now, I think at that time, the law of continuity was a principle or a law that had been invoked by Leibniz, and before him Kepler. Now, Kepler was from Stuttgart, as was Hegel. Hegel was sort of a great fan of Kepler's mechanics, celestial mechanics, and Kepler worked within the sort of Greek geometric thing, which Newton then converted into equations, right? And in various places, Hegel says he believes that Kepler is the great empirical-based sort of cosmological thinker, not Newton. He thinks that you can derive all of Newton's laws from Kepler's laws. He gets into a bit more contemporary thing. Jean-Louis Lagrange was an Italian, moved to work in France, famous elaborator of the calculus, and claimed to do it entirely algebraically. I mean, Lagrange famously boasted that there wasn't any diagrams in one of his famous texts. And Hegel had Lagrange's works and so on, he'd obviously read them. Lagrange's exposition of the rectification of curves, that's just the problem going from rectilinear things to curves, since it proceeds from the principle of Archimedes, involves the translation of the Archimedean method into the principle of modern analysis, and this affords us an insight into the inner and true meaning of an endeavour which in the other method is carried out mechanically. But Archimedes' principle that the arc of a curve is greater than its chord and smaller than the sum of the two tangents drawn at the endpoints of the arc and contained between these points and the point of their intersection does not yield any direct equation, right? So it doesn't get translated into this modern algebra. And there's no, via which there is the assumption that there are numbers that will give you the solution to these equations. Its translation into modern analytic form consists in the invention of an expression which is per se a simple fundamental equation, whereas in the earlier form, Archimedes' form, the principle simply demands endless alternation between terms, each time determined as too great and too small, the successive advance only yielding new terms which are still too great and too small, albeit between always narrowing limits. Okay, so he's on to this Archimedean approach. And in fact, there seems to be a big sort of backstory to Archimedes' approach. Archimedes, of course, is sort of well after Euclid, but Archimedes develops ideas that had been developed before Euclid and actually developed within Plato's academy by some of the major mathematical thinkers of the time there, especially a man named Eudoxus of Cnidus, Eudoxus, and Theaetetus, who's a subject of one of Plato's dialogues. So I just want to sort of say a little bit about this backstory to Archimedes that I'm sure Hegel was aware of. His descriptions of these within his descriptions of sort of mathematical quantities, he talks about ratios, and it's very clear that he's talking about the type of way ratios were described in Greek mathematics, not the normal sense of ratios. It's usually said that one of the sort of big discoveries in Greek mathematics, which had a totally devastating effect on the current sort of worldview, the Pythagorean worldview, was that there are what we call irrational numbers. Like we think of the number square root of 2, right? The number that when you multiply by itself gives 2. That's irrational, i.e. you can't represent it by a ratio of numbers. And the Pythagorean worldview had been that everything can be represented by ratios of numbers, everything. Right? The person who made this discovery is said to have been, the legend has it that he was drowned by the Pythagorean sect, so that the news of this irrationality of the world would not come out, and so on. That's the way that it's usually talked about, but that's sort of an anachronistic way of talking about it, because the Greeks didn't have the number, or didn't have the conception of a number, the square root of 2. It just wasn't a number. Numbers were either whole numbers, like 1, 2, 3, or ratios of those numbers, like 2 is to 3 or 3 is to 4, and so on. They didn't even think of those ratios as what we think of as fractions. That's what most historians of Greek mathematics tell us. But they did have these techniques, these sort of algorithms for working with numbers to give approximations of these values that they needed. You know, they did astronomy, quite advanced astronomy, and you need to have numbers like pi and so on, square root of 2, you know, for doing these calculations. And they had this trick, which is often attributed to Eudoxus. I don't know if that's what the evidence for that is. I don't even know if it's Greek. I mean, my guess is that it could have come from, you know, Mesopotamian mathematics, which was much more developed in terms of numbers and what we call algebra than were the Greeks. Could have come from Egypt, who knows? But the Greeks had it. And there's this simple way of generating this table to get approximations to here, root 2. And the rule is this. You just have two columns called one side and one diagonal, and they're the side and diagonal of the square, and you try to get the ratio of those. And you just start off with 1 and 1. And then to get the next side, you just add the side and diagonal of the line above to get 2. And to get the next diagonal, you add 2 times the side above and the diagonal. So 2 times 1 is 2, plus 1 is 3. And you just generate these numbers, just, you know, by a simple rule. Any sort of primary school child could do it, right? And as I said, they thought of these as ratios, and they could calculate with ratios. They didn't have expansions of the way we have. They didn't have decimal expansions, because decimal expansions rely on 0, right? So that's decimal expansions come from the non-Greek, you know, sort of Arab, Hindu-Arab sort of number system. But if you use it just to illustrate it, you can see how quickly you can get pretty good approximations to this, right? I mean, that was my pocket calculator, what it's spat out with root 2, it goes to 15 places. Of course, that's an approximation. I should have had ... there, because irrational numbers just go on forever, right? And you can't predict the next number, they just go on forever. So they're always approximations, but you can see you can get to pretty close to, you know, 4 decimal points or something like that within a few steps. And maybe that's enough for doing your calculations of the distance of the sun from the earth or whatever. But as I said, the Greeks wouldn't have thought about it like this. They would think about it in these ratios, and they would translate those ratios into diagrams. So they, as I said, they wouldn't think, where am I? They wouldn't think of it like that. They would think of it like this. They wouldn't say, with this triangle, by Pythagoras' theorem, you would get 1, 1, and root 2, they would say that the square that was built on the hypotenuse, the area of that square was equal to the sum of the area of those two squares. Right? That's how they'd express it. And they would say then there was a proof that the side of this square was incommensurable with the other sides. And there's various ways in which they prove them. I mean, the typical one that's usually talked about is a sort of reductio ad absurdum. It's a quite easy proof that you can do to show that. But again, they seemed, rather than what we think of as a reductio ad absurdum, they seem to rely on geometric ways of doing this. So that was root 2. And I want to suggest that this type of pattern quickly develops once you start going down that path. And it's easiest to show with these ratios that they're attracted to. The famous one, which sort of gets a lot of hype, the golden ratio. You get this sort of, the Parthenon, the Acropolis is constructed on the golden ratio, or plastic surgeons can promise to reconstruct your face so that the distance between your eyes and your chin is the golden ratio, because that's what George Clooney has, or something like that. There's this type, there's really hyped up stuff, but nevertheless, the golden ratio is an incredibly interesting mathematical object. And it's simple, but sort of complex. The golden ratio simply says you get a line, or line segment AC, and divide it in a way such that the ratio of the smaller to the larger part is equal to the ratio of the larger part to the whole. Now, if any of you know Plato's divided line in the Republic, you may think that sounds a bit like it, and there are many arguments that Plato has that in mind. Anyway, but apart from that, that's the golden ratio. It's sort of a little easier to think about if you just sort of pull that over here, and we have C to D as the same length as A to C. And then you would describe the golden ratio in this way if you were a Greek. You'd say the square built on B and C is the same area as the rectangle that you would get by having sides CD and AB. And that's called a geometric ratio. And that BC is called the geometric mean of the other two segments. Keep that sort of phrase in mind, geometric mean. It goes through, there's 700 odd occurrences of it in Euclid's Elements. But the other distinctive thing about the golden ratio, there's another mean involved. That's the mean between points A and D of C. And C is called the arithmetic mean of A and D. Here you're taking A and D as discrete magnitudes, as numbers, right? And C is just like the average of those numbers. So the weirdness of the golden ratio, it's a double ratio that involves both the geometric mean and the arithmetic mean. And that's going to be important for us because these are two of three means that the Greeks seem to be obsessed by, or at least some of the Greeks seem to be obsessed by, because they got them from music theory. The other one's called the harmonic mean. Okay, here's back to Fibonacci. There's a link between the golden ratio and this famous Fibonacci series. As you can see, it looks a bit like the link between the square and the generation of root 2. The Fibonacci series you generate in much the same simple way that you generated that other series, but here you just add the lines. You start off with 1 and 1, and you add them to get the next value. 1 and 1, 2, 1, 2, 3, 2 and 3, 5, and so on, right? So just a simple generation. And once you put them in terms of a ratio, they start to converge on the value, or the sort of numerical value of the golden ratio, which when I looked it up on Wikipedia or something, and they gave it to that many decimal points. Again, it's an irrational number that goes on forever. These don't converge quite as quickly onto that ratio as the ones with root 2, because it turns out that numbers have degrees of irrationality, and the golden ratio is the most irrational number. It takes longer to get to accurate sort of parts of it and so on. But you can see it's still doing pretty well, and it's got this under and over type of approximation. 1 to 1.5, 1.66, 1.6, 1.62, 1.615, and so on. So you're converging on this. Well, our way of talking on it, you say you're converging on this number because we think it's a number. The Greeks don't think it's a number because it's irrational. It's the ratio of two incommensurable magnitudes, and it's not a number. So remember Hegel on infinitesimals. This is all sort of sounds like he's alluding to this sort of area. Its translation into modern analytic form consists in the invention of an expression which is, per se, a simple fundamental equation, whereas the earlier form, the Greek form, simply demands an endless alternation between terms, each time determined as too great and too small, the successive advance only yielding new terms, which are still too great and too small, albeit always between narrowing limits. Now, in fact, recently there's been a lot of interest in this type of mathematics and its relation to Plato's metaphysics, and the most radical version of this is, that I've come across is this historian of mathematics, a mathematician in Athens named Stelios Negropontis, who believes that Plato's whole metaphysics is based on this type of stuff. That Plato's metaphysics is based upon this type of geometric way of approximating numbers in which you never get to the number, that was found, they think, early by Theaetetus, who was a young sort of guy working in Plato's academy. Anyway, I think Hegel's got a similar sort of approach. And the interesting thing about these, proving the irrationality of these numbers or proving the incommensurability, is that you produce these infinitely repeating figures, these sort of fractal type of figures. The easy one to see is the golden rectangle. That's a rectangle with sides, you know, of the proportion of the golden ratio. And you get the rectangle, and then you simply divide off a square, and what you're left with is another golden rectangle. Okay, so that bit up there is just similar to the big one. It's just stood on its side. And of course, this one up here is the same. That one there is the same, and it just goes on forever. And you may have seen these with, I mean, people often put a type of spiral in it, and you know, various claims are made about galaxies and conches and all that sort of stuff, which a lot are probably false, but the type of mathematical structure is itself very interesting. You get the same thing with the same proportions in the pentagon. Now, Theaetetus was famous for working on what are called Platonic solids, right? Generated from figures like pentagons and octagons or whatever. Now, the pentagon is really just like a square, but with another side. Okay, I mean, we looked at the square before and looked at the relationship between the side of the square and the diagonal. Well, this is a pentagon, which 5 sides, but otherwise it's like a square. I mean, you could think of a circle going through all those, and a square would just be 4 points in the circle, where this is 5 points, or you could have 6 or 7 or 8 or whatever. But with 5 points, and again, you look at the ratio between the sides and the diagonals, and the ratio turns out to be the golden ratio. Right? So the ratio between E, D, and G, D is the golden ratio. Or you could say that the diagonals cross each other, divide each other in terms of the golden ratio. And you get this famous sort of pentagram figure, which was used by the Pythagoreans as a sort of symbol of friendship or something like that, and became later associated with various mystical practices and so on. I remember a sort of a folk rock group from the 60s called Pentangle, where they used to have covers with sort of real sort of 60s stuff. And again, I mean, there's nothing about, I mean, you know, there's a sort of, we can see the mystery that this sort of, these diagrams have got, right? I mean, the diagonals make another pentagon in the middle. You draw the diagonals of those, they make another pentagon. And you do those, and they make another pentagon. And where are they going? Well, they're sort of going nowhere, right? I mean, they're just sort of continually going into somewhere, something. As I sort of alluded to before, the underlying maths of this seems to be based on these three double ratios that you find in Pythagorean music theory. This is from Plato's Epinomis, usually said not to be written by Plato, but it seems to have been written by one of his followers, and it's usually generally thought to reflect his views. Some people still think it might have been Plato. But he alludes to this sequence of numbers 6, 8, 9, and 12. This wonderful quote. The mean of 6 in relation to 12 are determined by the ratios 3 to 2 and 4 to 3. The sequence based on both of these means has been granted to the human race by the blessed choir of the Muses and has bestowed upon us the use and concord and symmetry to promote play in the form of rhythm and harmony. And they took this, the Pythagorean sort of culture took this very seriously, right? That these ratios were somehow thought to regulate the city. In fact, there's interesting, Aristotle's Nicomachean Ethics has this famous thing about forms of justice, which looks like it has three parts, and the three parts look like they line up with the arithmetic, geometric, and the harmonic means taken right out of Plato. Just to give you, I mean, if this is all sort of a mystery to you, it's pretty easy, but it's sort of easy to get confused about these things. Here's my sort of version of a Greek monochord in which you divide up strings and pluck them and see what the relation of the things are. So the music theory is about getting consonant intervals, right? Harmonious intervals, differentiating them from dissonant intervals. And they recognise the most harmonious interval was the octave, and if you've ever played around with a guitar or something like that, that occurs at halfway along the fretboard, or halfway between the nut and the bridge, right? I mean, so you pluck that and you get a note, if it's in tune, E, and you put your finger on the 12th fret and you get E above it, next highest. If the fretboard went up further and you put your finger on the 24th, you'd get the next E above it. And this is a geometric series. But it's weird. Though, okay, if you had songs that only had, you know, the octave in it, that would be pretty limited, right? So you need to divide up the octave into consonant intervals. And the Pythagoreans thought there were only two really consonant intervals within. That's what we call the perfect fourth and the perfect fifth. So, you know, do, re, mi, fa is the fourth, and so, right, is the fifth. And they're, to anybody's ears, they're consonant intervals, right? Now, the interesting thing is you can't get a consonant interval by applying the geometric mean within the octave, because if you do so, you get what was in medieval times called the devil's note, which is thought of as the most dissonant note on the scale. It's the one that, I don't know if they still do, but in Europe, sirens on, you know, police cars and things like that, went da 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 da, and it makes you tense, right? That's the whole thing about the tritone. It makes you tense. Scary movies use the tritone, that sort of stuff. Right? So you can't get just the consonant notes by repeating this geometric structure inside the octave. You've got to use these, and these turn out to be the arithmetic and the harmonic means of them. And they have their own, the arithmetic works like this. I won't worry about that. Yes, we will. The geometric mean is simply, for us, the two terms is the square root of their product, as we discussed before. The arithmetic mean, as we discussed before, is just the average. So 9 is the average between 6 and 12 in that sort of thing called a musical tetractys. And the harmonic mean is interesting. It's actually mathematically it's the inverse of the arithmetic mean, but it's not obvious when you look at it. It's like that, but you get it by that sort of equation. And the harmonic mean of 6 and 12 is 8. And interestingly, if you sort of think about a guitar fretboard, if you're going up the board, I mean, the arithmetic mean is the harmonic mean of coming down the fretboard, right? I mean, they're complementary. They add up on the fretboard, although that's an arithmetic relation. Harmonically, it's a geometric relation. A fretboard is like a logarithm. If any of you can remember slide rules, probably not. When I went to school, we used slide rules and log tables, right? And slide rules and log tables are a way of translating between arithmetic and geometric relationships, and that's what the fretboard does. And that's what these are doing. They're inverses. Now, that gives these sort of three relationships all these interesting properties, such that for any two extremes, x and y, the harmonic mean is less than the geometric mean, which is less than the arithmetic mean. But there's something really weird. I mean, and the interesting bit is this. For the same interval, the geometric mean of x and y is actually the geometric mean of the harmonic mean and the arithmetic mean of x and y, right? And that you can just repeat this over and over and over. So if you're looking on a sort of a graph, at 6 and 12, 8 is the harmonic mean of 6 and 12, 9 is the arithmetic mean of 6 and 12. The geometric mean is the sort of square root of 6 by 12, 72, 6 times root 2 or something like that. When I did it on my calculator, it came out as 8.4852. So 8 and 9 are giving you a sort of very rough approximation of the geometric mean. But when you take the arithmetic mean and the harmonic mean between 8 and 9, right, you get now a very narrow interval, 8.47 and 8.5, and that's a much better approximation of 8.4852. And of course you can do the same again, do the same again, you can do the same again, do the same again, do the same again, right? Forever. But you're not going anywhere, you're not headed towards a value. And I think Hegel's point is that this is the difference between the ancient way of doing this and the modern way of doing it. Remember, because of law of continuity, the vanishing magnitudes still retain the ratio from which they derived before they disappear, right? These are maintaining the ratio. The ratio stays the same, although they're different sequences of numbers. The ratios stay the same in as much as that they produce the same geometric mean constantly. It's not the same ratio in what we mean by the same ratio, but it's what the Greeks, that's one sense of being the same ratio for the Greeks. So, remember Hegel's phrase, I said that, didn't I? What is it that we're going into as we sort of plunge further and further into this interval via the pairs of the arithmetic and harmonic means? Well, I think nothingness would be a pretty good word for it, an appropriate description for it, and this conception of nothingness is not dependent on the number 0. Right? There aren't any numbers, as it were, that are inside there. That, in the modern sort of sense, there's this type of infinitely dense a lot of numbers and you're trying to. And this fits with the idea that, I mean, becoming is not to be thought of as the becoming of something, right? I mean, in the modern way, the becoming of these increasing approximations is headed to the being of a number, a real number. But the Greeks don't have that real number. They don't, and Hegel doesn't want that real number. He wants to maintain this idea of incommensurability, being, well, he wants to, I think, retain something like the idea that Plato seems to have, that something like the geometric mean is not a number, but it's something like an idea. And it's an idea that's approached by actual numbers, these two arithmetic and harmonic means, which are straightforward numbers, you can write them down. So you get this increasing approximation to something, but there's nothing that they're approximating. Okay, so yes, that's it. Thank you.
Well, I'll ask a question. You go first.
No, you can go first.
Yeah, it was just a question on the different versions of calculus of Newton and Leibniz.
Right.
So obviously, the way Newton presents the terms is in terms of fluxions and fluids.
Yes, that's right.
So his way of even representing the magnitudes involves this tension towards something,
Yeah.
but not necessarily with an end in mind either.
Right.
I wonder if Hegel has any discussion on the qualities of Leibniz's version, which is this more modern version,
Yeah.
and Newton's, which looks a little bit Greek and Heraclitic,
Yeah.
actually.
Yeah. I mean, Hegel is much more favourable to Newton than one would expect. He thinks that Newton's maintains this connection much more fundamentally to the Greek sort of approach. And as you say, I mean, the sort of typical way of reading it is that, oh, that didn't really go anywhere. There was the sort of, the British got stuck with that. And then famously in the early 19th century, there's this sort of group of Cambridge people that sort of said, let's get rid of this and import all the continental stuff, which is the way to go. Hegel thinks that Newton was on the right track, but he thinks that Newton's idea of limit, there was still a problem with the idea of limit. So that's why he's much more critical of Lagrange and people like that than he is of Newton. He thinks that's a straightforward algebraic sort of Leibnizian.
Thank you, Paul. In the beginning of the talk, you described what Hegel says about being, and then nothingness,
Right.
and then becoming,
Right.
in which being and nothingness vanish into each
Yeah.
other. And that was a bit confusing to me, because I would normally assume, think about becoming as something where a non-existence of something is actually involved, rather than say nothingness. So, Graham was talking about the difference between nothing as the noun and as the quantifier. And I would think about becoming as something where the quantifier is involved rather than the kind of noun stuff.
Yeah.
So the question that I have is that how does Hegel differentiate, say, non-existence from nothingness in order to talk about becoming?
Yeah. I mean, Hegel wants to sort of maintain that coherent notions of being and nothing depend on becoming, not the other way around. Right? It's becoming that becomes the sort of main concept, and then it moves into its own dialectic. But we're not supposed to think of becoming as built out of being and nothing, as if they're independently meaningful. To show that they're not independently meaningful, I take it that the collapse of being into nothing is meant to show that, right? It's a sort of an intolerable opposition. So, but it sort of makes some sort of sense to say they're moments of becoming. Now, you don't get very far with, I mean, the sort of thing about Hegel is there's another sort of 760 pages or something to go. And you're not going to, I mean, I don't think he wants you to sort of dwell on the being, nothing, becoming terms. I think he wants you to just go along and see where that leads. For example, one of the it becomes obvious somewhere at the end of book 2 that where he talks about modality, and it becomes clear that something like possibility is the equivalent of nothing. It's when you talk about modality, right? What is mere possibility? Well, it's nothing as much as that doesn't exist in the actual world. But he wants to build in possibility as something within reality, in the way that nothing is built into becoming, right? So it's sort of, you're supposed to go along with the sort of flow of this, I think, and you're not supposed to worry too much about it. It's like there's a very, very limited language that you're talking about if you've just got being, nothing, and becoming. You're not going to be able to say much. In fact, you're not going to be able to say much more than he says. That's the idea, I think.
Just as a quick follow-up, does it mean that he is trying to maybe distance himself from the substance style ontology and go into kind of becoming, kind of process style ontology where nothingness and being are part of becoming first?
He certainly wants to get away from the substance ontology. Yeah.
Thank you.
How becoming. You know, he's not Heraclitus, right? But he's very sympathetic to Heraclitus, right? The next move you get is that you just sort of can't say becoming is what is, right? Because it's things that become, it's determinate things that become. So it needs to be more made. The concept needs to be more determinate by new concepts and that sort of thing.
Okay, so I have Graham and Danielle and then lunch.
This is just a very small observation. I'd have to go and check where it is that Hegel says this. But at one point, and I guess it's in the logic, he actually says the infinitesimal is the contradictory union of the continuous and the discrete.
Yeah.
So if you, the discrete is the point, the continuous is the line. And he says if you think of these as the first two elements of a triad, then the infinitesimal is that pair aufgehoben.
Yeah, I mean that would fit, I think, with what he says in other places. I mean, I don't recall that passage, but it sounds like
where it is.
Yeah.
I can dig out the reference if you.
Right.
If
It sounds. He's very interesting on the discrete and the continuous, right? Because he thinks that each of those concepts have the other built into it. He thinks that numbers, discrete numbers, have continuity built into it. As in, I think the idea is that the ordinal series of numbers. This is a sort of 19th century idea that or the continuity or the order of numbers is a type of primitively geometric notion. So it's, for a full account of numbers, you need a sort of geometric way of thinking. But for a full account of geometry, you also need an arithmetic way of thinking. He's critical of Schelling in an interesting way, because Schelling thinks of geometry as it were, and arithmetic as sort of derivative. And Hegel's very critical of that idea. He wants to think that arithmetic and geometry sort of equally presuppose each other. So as if arithmetic wears the sort of discrete on its surface and presupposes the continuous, and geometry wears the continuous on the surface and presupposes discrete. So I think what you say about infinitesimals would reflect that sort of thing. So thank you for that observation.
Thanks, Paul. I'm quite taken with this idea that he developed, that he's sort of insisting on this approximation of nothingness.
Right.
But I'm struggling to see what that means for his way of thinking more broadly.
Right.
So it's a huge question, but perhaps you could give an example by going back to one of your very first slides where you had this identical treatment of being and nothing, and say how we actually were to read this perhaps differently if we keep this sort of take on mathematics in mind,
Right.
if there is such a thing.
Okay. Look, I think I can only sort of more or less repeat the idea that something like this. They were the initial instantiation of this peculiar underlying idea that runs right through it, which is sort of like the metaphysical idea of the identity of identity and non-identity. That's the way he expresses it somewhere, but he expresses it in different ways. Identity of difference, that sort of thing. It's a way of conceiving of the identity of two things that nevertheless are in some sense incommensurable. Right. So the identity of being and thought, or something like that. The identity of that you have to reproduce, you have to hold on to the sense in which they're different, right? But you have to, given the differences there, you've got to have a sense in which you can conceive of a unity of those things. Now, I think this stuff about geometric, arithmetic and harmonic means is a sort of early instantiation of that. It's a sort of mathematical model of it. And of course it plays into that point that Graham raised, right, a bit about the sort of relationship of arithmetic and geometry. So we know he's against analytic geometry, right? He's against the idea that you think of a line just as a sum of points that you can write down as numbers, or pairs of numbers. He thinks that presupposes this continuity, which is really a geometric notion. But equally, he's sort of critical of Schelling. He thinks Schelling just accepts the truths of Euclidean geometry, and I think Hegel doesn't. Hegel's he's aware that things are happening in geometry in the early 19th century, which are quite radical, apart from, which lead to things like non-Euclidean geometry. He possesses a book by this guy Lazare Carnot, who's an early French projective geometer. He's very keen on Kepler, who is usually thought of as a sort of a prelude to this discipline of projective geometry, which comes in the 17th century, Desargues, which is a sort of an alternative to Descartes' reduction of geometry to arithmetic. And it flourishes in the 19th century in interesting ways after Hegel. I mean, Hegel doesn't fix it, but I think Hegel's onto these. There's enough in his understanding of the Greek origins of these relationships and things that are happening at the time in geometry. He's got these books and so on. To think that there's some important philosophical dimension to this, which can be used as a critique of the type of modern analytic way of thought. It's not trying to dismiss the analytic way of thought. Certainly not trying to dismiss Newton. It's often said that he thinks the planetary motions are by the music of the spheres and that. I mean, that's really crap. I mean, he's really got sophisticated ideas about cosmology and the role of Kepler and things like that. It's all about the logic of cosmological explanation. It's not about whether he thinks that there are numbers. And as I said, I mean, in sort of current Plato studies, there's this real push towards reinterpreting Plato in a totally different way to the way we think about Plato, right? He's this person who thinks that ideas necessarily come with instances that appear in these sort of oppositions, and that for any idea there's better instances of them that can be seen in these, but none of them actually embody the idea and so on, right? And this idea that he gets it from Theaetetus and whatever. I do think that Hegel's sort of onto these ideas by his bizarre interests, his deep interest in Greek philosophy and the mathematics that he thinks is going on in the academy. And his familiarity with all these, I mean, we've been sort of talking about the Neoplatonists. He's certainly familiar, and he's certainly into the type of mysticism and whatever of the Neoplatonists. But he's also into the mathematics that you get there, which is quite considerable. Proclus is usually now described as one of the most important theorists who brought all the ancient mathematics into European culture. There were various, before people like Newton and Isaac Barrow, there's a whole lot of people who sort of bring Proclus to bear on these sort of things, and they seem to be taken up by Barrow and Newton. Thank you.
Meet back here at 10 to 2.
Thanks, Paul. That's great. I will eject you.